In this video, we will study single phase induction motor. So let us see what is single phase induction motor. Single phase induction motor, it is very similar to three phase induction motor. But here instead of giving three phase supply to the starter, here we give single phase supply. Now we see what are the advantages of using single phase system. The single phase power system are more widely used than the three phase system for domestic purposes, commercial purposes and some extent in industrial also. Because the single phase system is more economical than three phase system, the power requirement is most of the houses, shops, offices are small, which can be easily met by a single phase system. The single phase motor are simple in construction, cheap in cost, reliable and easy to repair and maintain. Due to all these advantages, single phase motor finds its application in vacuum cleaners, fans, washing machines, centrifugal pumps, blowers, washing machines, etc. It is also known as fractional kilowatt motor due to its small HP ratings. Then come to the classification of single phase motor. Single phase motor are briefly classified into four types. Single phase induction motor, AC series motor or also named as universal motor. Third, repulsion motor and fourth, synchronous motor. Single phase induction motor is again classified into three types. Split phase type, second capacitor type, third shaded pole type. Repulsion motor, it is classified into two types. Repulsion start induction run motor and repulsion induction motor. Synchronous motor is classified into two types, reluctance motor and hysteresis motor. Next, come to the construction of single phase induction motor. Likewise, any type of electric motor, single phase induction motor also have two main parts, rotor and stator. Rotor is the rotating part and stator is the stationary part. A single phase AC supply is given to the stator. Stator consists of field winding and rotor consists of armature winding. A single phase supply is given to the stator and the rotor is connected the mechanical load through the shaft. Basically, the rotor of single phase induction motor is squirrel cage type. It is of squirrel cage type three phase rotor. Like three phase induction motor, squirrel cage three phase induction motor, in single phase induction motor, rotor is of squirrel cage type. And the construction of single phase induction motor, it is almost equal to the squirrel cage three phase induction motor, but in case of single phase induction motor, the stator has two windings instead of three phase induction motor, the stator has three phase winding. Here the first diagram shows the winding diagram or representation of a single phase induction motor. Here the second diagram, it is the outer frame which consists of the stator or the stationary winding and the rotor is of squirrel cage type. Here see, it is of 2 pole single phase induction motor, the first figure. Here the pole core, it consists of the winding named as field winding, to which single phase AC supply is given. Then this figure also shows the cut section of a single phase induction motor. Here it is clearly visible. In the second figure, the slots are there in the stator in which windings to be wound, and the rotor is of squirrel cage type. Here the construction of stator of a single phase induction motor has laminated stamping. Like it is as we study that single phase induction motor is very similar to the 3-phase induction motor. So I give here the idea about the stator of a single phase induction motor because very long day past I have taught about the 3-phase induction motor. So just for your remember, I just review that part, how the stator constructions are there in case of 3-phase and also in case of single phase. So I go back to the diagram. See, this is the stator, this is the stator one, which one is laminated to reduce the eddy current. The second figure, I show the second figure here. This is the, in the first figure, this one is the stator, and in the second figure, this outer one blue color, this blue color structure is the stator, and which is laminated to reduce the eddy current loss. And it consists of many number of slot. It provides many number of slot on its stamping to carry the stator winding, also known as the main winding. Here it is clearly visible in the first diagram. This brown color, this copper wire, these are the stator winding, and stampings are made up of silicon steel to reduce the hysteresis loss. When you give AC supply, okay, here in this diagram it is clearly visible. When you give single phase AC supply to the stator winding, okay, the magnetic field is created due to the flow of current, alternating current in this winding. What happened? Magnetic field is created with speed is equal to the synchronous speed. Ns is equal to 120 F. Ns is equal to 120 F, due to which the rotor, like in case of 3-phase induction motor, here also due to this MMF, it also links with the rotor winding, and the rotor rotate little bit less than the synchronous speed. Hence it is also known as asynchronous motor. Next, the construction of stator of the single phase induction motor is similar to that of 3-phase induction motor as you study, except what are the dissimilarities? The dissimilarities are, the first dissimilarities is that the single phase induction motor are mostly provided with concentric coils. Why to use concentric coils? Because it is easy to change the number of turns per coil with the help of concentric coil, and the MMF distribution is also sinusoidal here. And the second is, except for saddle pole motor, the single phase induction motor, also named as asynchronous motor, has 2 stator windings, namely main winding and auxiliary winding. Instead of using single winding, here 2 windings are used in the stator, main winding and auxiliary winding. This auxiliary winding, it is also named as the starting winding. These 2 windings are placed in space quadrature to each other. It means the phase difference between these 2 windings is 90 degree. Then come to the rotor construction. The rotor construction of single phase induction motor is very similar to the squirrel cage 3-phase induction motor. I review the three-phase induction motor rotor construction here. So I want to tell you the some points. The first point is that the rotor is cylindrical and has slotted all over its periphery, as you see in the previous diagram. The slots are not made parallel to each other but are little bit skewed, as the skewing prevents magnetic locking of the stator and rotor teeth and makes the working of induction motor more smooth and quieter. It means to reduce the noise. It is made somewhat squeal. Then second, the squirrel cage rotor consists of aluminum, brush or copper bars. These aluminum or copper bar are called as rotor conductor. As you see in the previous diagram, I go back to the diagram. See here, this is the cylindrical type rotor, this one is the cylindrical type rotor, and here at both the end two end rings are there and they are shorted by a aluminum or copper bars, which one is written here also. Then the copper and aluminum ring permanently short the rotor conductor called the end rings. To provide mechanical strength, these rotor conductors are brushed to the end ring and hence form a complete closed circuit, resembling a cage, and hence got its name as squirrel cage induction motor. As end rings permanently short the bars, the rotor electrical resistance is very small and it is not possible to add any external resistance as the bars gets permanently shorted. The absence of slip rings and brushes make the construction of single phase induction motor very simple and robust. Then come to the working principle of a single phase induction motor. See, when you give single phase AC supply to the stator winding of a single phase induction motor, the alternating, this one is again I have explained in the diagram part also, same thing I will explain here. See student, when you give a single phase AC supply to the stator winding, at that time what happen, alternating current it starts to flow in the stator winding, also named as the main winding. This alternating current produces the alternating flux called as the main flux, and this main flux also links with the rotor conductor which cuts the rotor conductors. Hence EMF is induced in the rotor. This is due to Faraday's law of electromagnetic induction principle. As the rotor circuit is closed, hence current starts to flowing in the rotor, and this rotor current, according to the Lenz's law, you know that the effect opposes the cause. Hence the rotor current, which one is flowing through the rotor due to the field created by the rotor, its direction is opposite or it opposes the stator MMF which produce it. Thus the axis of the rotor MMF wave coincides with the stator field. Hence the field created, again here I repeat, hence the field created by the rotor and stator, they opposes to each other. Therefore the torque angle is 0 and no torque is developed at the starting in case of single phase induction motor. Thus single phase induction motor is not a self-starting motor. However, if rotor of such motor is started by auxiliary means, the motor is quickly attains the final speed. And this behavior of single phase induction motor can be explained on the basis of two theory. The first named as the double field revolving theory and cross field theory. And this one is, students, you also noted in your home. Suppose in your home sometimes if ceiling fans are not run, at that time you just give a, or due to the discharge of the capacitor or charging down of the capacitor, if you just give a jerk to the fin of a fan, ceiling fan, it starts to rotate. So due to give some external force to the single phase induction motor at the starting, it gains the speed. Okay, and this type of behavior of single phase induction motor is briefly explained by the two theory named as the double field revolving theory and cross field theory. So student, in the next video class we will see what about this double field revolving theory and cross field theory. And before going to that second part, that is double field and cross field theories, we see the one principle called as Ferrari's principle. What is Ferrari's principle? This principle is invented by the Galileo Ferraris, the Italian physicist who established the basic principle of induction motor, which is now the principal device for the conversion of electric power to mechanical power. So what is this Ferrari's principle? For this, here student, I have shown one diagram, one phasor diagram. Here see this x-axis, it represents the flux. This x-axis, it represents the flux created by the stator. Okay, this Ferrari's principle. And how you get the total flux? See, I have explained it with these mathematical expressions. See, the magnetic field which one is produced by the single phase induction motor through a single phase alternating current is an alternating magnetic field, which can be, suppose in the x-axis I show that flux, magnetic flux, suppose it is phi. Okay, this one. So according to this Ferrari's principle, it is resolved into two components, A1 and A2. It is the flux which one is produced by the stator due to the supply of single phase AC. Let it be represented by x-axis, and according to this Ferrari's principle, it is resolved into two components, OA1 and OA2. Okay, and they move along the same axis OX. OA1, it is in anti-clockwise direction, and the movement of OA2, it is in clockwise direction. And this OA1, the component of this flux, this magnetic flux created by the stator, we resolved it into two components. This A1 and A2 have same magnitude H. Okay, and they move clockwise and anti-clockwise with the same speed, omega radian per second. Suppose at standstill, it means at theta equal to 0, both OA1 and OA2, they lie in the axis of OX, and after some time t second, OA1 placed by an angle theta equal to omega 2 in anti-clockwise direction, and OA2 it placed by a angle theta in clockwise direction. Let you assume that this OA1 it is a backward flux, and OA2 it is of forward flux. Okay, and Now we resolve the component of OA1 and OA2. If we resolve the component of OA1 and OA2, then one component of OA1 comes along the axis of x and another component comes along the axis of y. Similarly for the component of OA2. And finally, if you find how much resultant flux comes under x component, or the resultant flux along the x component is OA1 cos theta. This is the component of the flux OA1, and plus OA2 cos theta. This is the component for the flux OA2, which gives 2h cos omega t. Similarly, along y axis, this axis y axis, the resultant flux along y axis is equal to OA1 sin theta, because OA1 is upward direction. If we resolve this component, the perpendicular component is along y axis, and the component of AY2, the vertical component of OA2 is downward, this downward. So what be the resultant flux? OA1 sin theta minus OA2 sin theta. As the magnitude is same, so it is h sin theta minus h sin theta. In place of h you may write also phi. So the resultant flux along y axis or the y component is 0. From this study, students, it is very clear that the resultant magnetic field is 2h cos omega t along x-axis, and along y-axis it is 0. Okay, so it is therefore clear that the two rotating magnetic field traveling in opposite direction with the same angular velocity result in an alternating field of twice their amplitude. And second thing, an alternating field can be replaced exactly by two rotating field of half its amplitude traveling in opposite direction at synchronous speed. So based on this, student, in our next video class I will explain what is double field revolving theory and cross field theory. Thank you.